We will now turn to analyses using Mplus, and we're going to start without covariates. That is, in the reading data we're not going to use the poverty covariate but only the 5 latent class indicators at each of the 4 time points. So we have 20 binary observed variables, and we'll start with regular LTA, which I discussed the ideas of in the example section up here, which is in segment 2, slides 3 to 9, and also discussed in more technical detail within the basic building blocks section. So focusing on regular LTA, let's take a look at actually running Mplus, and we will first take a look at how you specify HTML style output, which provides an easy way to navigate through the output via links. And we're going to find where we see the replications of the best log likelihood shows up and take a look at error messages. We're going to note the number of parameters, log likelihood, and the big class probabilities and entropy. And then as a first step, we're going to interpret measurement parameter results in the probability scale, because we want to assure that we have the latent classes in the order that we want them to be for interpretational purposes that we find being the best for the actual application. And if not, we're going to turn to the new feature of automatic class reordering, which was introduced in version 8.5, and that uses opt-seed and a new s-values feature, and I'll show you how you operate with those. This is described also in the Mplus version 8.5 language addendum, which you find where the user's guide is posted. And then we're going to interpret class and transition probability results in odds and odds ratio scales and take a quick look at some of the technical output. Now you can go to outputs 1 and 2 for this Webtalk, which you find at this address. I'm going to get there in a different way. I will take a look at Mplus here. And first of all, I'm going to show you the Mplus menu, the drop-down menu, where you see these options of using the plain text output, which many of you use, I think. But I'm going to work with the HTML output, as I mentioned. And you can click back and forth here, and the selection will stay. And this is what you do before you do the analysis. Now let's open the first analysis. So the file type here is HTML, and we're going to take a look at the regular LTA output. And you note then that you have these backwards and forwards arrows that we're going to use, and you have these magnifying glasses where you can make the font smaller or bigger, or the third one here resets the zoom to normal, no zoom. The fourth one is sets the current zoom level as a favorite, and the fifth one jumps the zoom level to your favorite zoom level, that is if you want to use it on the next output. So let's take a look at the input instructions here. I'm not going to go through the basic parts of Mplus input, except to note that we have a title, data, and variable command. And use variables here specifies the 20 binary variables at time point 1 with suffix 1, time point 2, time point 3, time point 4. That's the order in which they are given. And we declare all of them as categorical. And then we have the 4 latent class variables C1 through C4. All of them have 3 classes. That's our hypothesized number of classes. And we're going to do a mixture analysis, and we're going to choose a modest number of random starting values to ensure that we find the global maximum for the likelihood. And you note that I have these numbers divisible by 8, that is the number of processors that I use on my computer. So in the first stage optimization, you're going to get 10 sets of iterations per processor, and in the second last stage you're going to get 2 per processor. So you see that arranged and activated on your screen output as the optimization starts. Doesn't have to be divisible by 8, but it's nice. And you notice then that the ratio between the second and the first is like approximately 1:4, which I tend to use. And then the model is, in the overall part, you regress C2 on C1, the latent class variable at time 2 on the one at time 1, C3 on C2, C4 on C3. And then you get into the time-specific model statements, model C1, model C2, model C3, and model C4 here at the bottom. And the binary latent class indicators are these letter recognition at time point 1 to the words in context time point 1 with 1 threshold each because they are binary variables. And we give them parameter labels 1 through 5. There are 5 parameters listed in this list. If you look at the list of the use in the use variable part, you see that they are listed consecutively. So that list corresponds to 5 parameters. And we let them be different. We let those thresholds be different at the second, for the second class, you give them different labels, and for the third class. But these numbers, 1 through 15, get repeated across all the other 3 time points to ensure that we specify measurement invariance across time. And then we can choose various output here. I typically work with Tech 10 and Tech 15 for a latent transition analysis. And you can take the back arrow, come back up here, and it's always good to look for input errors and warnings, and there are none. And we actually then below that have the summary of analysis, which is always good to look at. Sample size here, 3,575, that's right. Number of dependent variables should be 20, 5 times 4. And there are 4 latent class variables. And we use maximum likelihood with a robust estimation of the standard errors. Now we may want to take a look at the univariate proportions, but we're not going to do that now. Instead, let's go to model warnings and errors, that section. That starts with the random starts that we have done, the analysis, the various analyses for different starting values, and their log likelihood values are listed here. And you see that the best log likelihood is replicated throughout all of those. So we have a nice stable solution. And we see then that second column is the seeds. So this value we're going to remember for reasons that will become apparent. And below that we see that the best log likelihood has been replicated, and it says to rerun with at least twice the random starts. You don't have to do that because we already have a good set. Otherwise we always print this out, so you can end up in an infinite loop here doing this otherwise, if you don't ignore it. More importantly, you have this error message, which is very common. That is that the thresholds get fixed at very large values corresponding to probabilities of 0 and 1. So that's innocuous rather, and actually it's not bad at all. It's preferable that probabilities become 0 and 1. It often makes the interpretation easier. A more important message is this: one or more multinomial loaded parameters were fixed. To avoid singularity of the information matrix, you do not want singularity of the information matrix, because then you don't get any standard errors. Now it's listed then what the problems are. We're going to take a look at that, and we're going to see that in this case that's also innocuous. It corresponds to 0 transition probabilities, but we're going to wait a little bit with looking at the details of that. And then you come down to this part of the output. Chi-square tests cannot be computed. That's has to do with frequency table tests with Pearson and log likelihood ratio chi-squares. I'm going to talk about that later on in the Webtalk. Model fit information. Here you note then how many parameters you have, what the log likelihood value is, and I tend to focus on VIC rounded up to Don't include the decimals there. There are enough digits anyway. And then I looked through the final class counts and proportions for each latent class variable based on the estimated model. We have simplified the output, moved some of the other output to the technical parts of the output, so to keep it clean. And you want to look at this first here to see that no classes have exactly 0 people or proportions in them. So this looks healthy. And we notice that we have a high entropy here. And then below that comes, as the next thing that you want to look at, latent class indicator means and probabilities for each latent class. And here, since we have binary latent class indicators, these are probabilities. So you have letter recognition, beginning sounds, ending sounds, cite and words in context. And you have the 3 classes. And here then we note that the first class has high probability for getting the item right, except for the last 2 items. So that looks like, for those of you who followed through the example in the beginning, that looks like the second class, medium proficiency. This then corresponds to the low class because you have very low probabilities to get the item right, that second category here. So that's the first class, that is the low class. And the third here has high probabilities almost all the way down to the more advanced item, and therefore that's the high class. So we have them ordered as medium, low, high, where we want them as low, medium, high. So we want to reorder here before we go on and interpret things. You don't want to look at latent transition results for classes that are mixed up in their order this way. It's just hard to interpret. So we want to put the class that appears second, this one, we want that to come first, and the class that appears first, we want that to come second, and the class that appears third should stay third. That means that the reordering should use the numbers 2, 1, 3. That is, second class should come first class should come second, and the third class should come last. 2, 1, 3. So we're going to remember that, and then the opposite as well for doing the reordering of the classes before we go on. So that means we're going to go to output number 2 in HTML form, regular LTA reordered. Here you have it. And how do the input instructions change them? Well, the only 2 things that change is that now we work with the opt-seed option here. So no, not asking for a bunch of random starting values, but just the optimal starting value set that gave the best log likelihood. There were several of them, but we just picked the top one. And here's the number that we were looking at before. So you give that number, and the only other thing you do is give these S values. The 2, 1, 3 order at all 4 time points with that bar in between of the time points. You could, for another application, you don't have to have the same number of classes, and you can even use this for latent class analysis where you have only one latent class variable, so you only have one of these sets. And then I tend to ask for Tech 8 as well, because I want to be sure that the optimization is done, gets to the same log likelihood value that the initial run came to. The reordering of classes does not change the best log likelihood value, nor does it change the number of parameters. So let's take a look at that then, going back up and going to Tech 8. So you have them first an optimization, log likelihood, the apps change in the log likelihood over the iterations. They should always be positive. And it comes to this value. That looks like the likelihood that we had before, given in scientific notation. And then you have the reordered optimization, and it reaches the same log likelihood value here. So the reordering has worked here. There will be situations where it doesn't, so you have to look out for that. So then we go back up to the top here, and let's take a look at what else we want to see. We are back at the warning, so we're going to say something about this. These are 1, 2, 3 parameters that are fixed, and we're going to see why in a second. Here we have the model fit information. Sorry, jump by. And we have the same log likelihood, same number of parameters. And now we have the latent class proportions given here in a good order. So at time point 1, fall of first grade, 69% are in the lowest class, 28% in the medium class, and only 2% in the highest class. And that changes then over the time points, so that at the end of first grade, only 4% are left in the poorest class, lowest class, and 81% have moved over to the desirable class. So let's look then to verify also that the class reordering worked. So this should be the lowest class. So we see the low probabilities for category 2. So the items are 0, 1, but they get reordered as 1, 2, 1, 2 per Mplus default. So second class then should have low values for the last 2, and it does. And the third class has higher values for the last 2, which it should have. And these profiles, these probabilities are the same across the time points, because we have measurement invariance here imposed, and you can check that they are the same. And then we can finally go down to latent transition probabilities based on the estimated model. So here you have C1, C2. So the rows are the classes that you're in fall of first grade, and the columns are where you are in spring of first grade. So you have a 34% chance of staying in the lowest class, but a 65% chance to move from the lowest class to the second class through the kindergarten year. And some kids are in the second class when they start and stay there with a fairly high probability. Fewer of them move on to class 3 already by the end of kindergarten. So those are the transition probabilities. Now you can ask, well, is this really significantly different from that? And how do you measure that? Well, what statisticians tend to do is, instead of looking at probability differences, they look at odds, the odds of being in second class versus the first, which is just a ratio of those two probabilities. And you have them here then, that ratio. So here it is, transition table odds for C1 to C2. And you compare, in this table, you compare to the diagonal. So the reference class is the diagonal class 1, 1, 1. So looking at the first row, and we go through this in detail in the basic building blocks technical section. So this 1.92 is the ratio of those two probabilities that we just looked at here, 0.649 divided by 338. But now we also get the confidence interval, 95% confidence interval for this, going from 1.751 up to 2.104, which does not include 1. Hence, this is a significant odds, significantly greater than 1. And this is a non-symmetric confidence interval, which is what you need to have for odds, also for odds ratios, and for probabilities also, for that matter, because they don't have normal or symmetric sampling distributions. So here you have the odds for moving on, almost an odds of 2, that is 2 times higher probability to move on than staying in the same class. And then you can look and interpret all the other odds here up to down here. Say this is moving from fall of first grade to spring of first grade, and you compare to staying in the same second class here versus moving on to the third class during this first grade. And the odds are pretty good for moving on to the second class, 6.543. And once again, the 95% confident interval does not include 1, so it's significant. Now we also have in 8.6 see specific classification results. So for each latent class variable, you get an entropy, 88 for the first, and you get these classification logits that we use for multi-step estimation in Web Note 21. And so 89 here, a little higher for second time point, 88 again, and 93 highest for the last time point. We have good classification there. What else do we want to look at? So let's see here. You get the model results. Now in version 8.6, I really wanted to rearrange things in the order that an applied person wants to look at things, to learn about things. So the model results, which is what usually comes first, are given here in the usual logistic regression type of parameterization. So you look at logits, which are not always easy to interpret. Going from logits to thresholds in logit form to probabilities takes a little conversion in your head. Likewise, when you look at the regressions here, C2 and C1, it's easier to look at measurement probabilities and transition probabilities, and therefore I prioritize that in the output in this case, as opposed to other Mplus situations. Now, let's take a look at some of the other things. Tech 15 here has several subsections, and we're going to focus on final class counts for the latent classes based on the estimated model. So here you have the latent class patterns. So here is a child that stays in the lowest class throughout the four different time points. And here's one that moves to class 2 at the end. So the entries here are classes, and there are 4 time points. And here you have the most common path throughout the years, or the 2 years, the 4 time point. Starting in the lowest class, move to second class at the end of kindergarten, stays there over the summer to the fall of the first grade, and then moves to class 3 by the end of first grade. 33% of the subjects do that. So that's where we find the information in the table that I talked about in the example section. Let's see, is there anything else that we want to discuss? I think that's it for these 2 runs.